We're going to work through some of the main examples in section 4.6, and you'll see that the focus of the section is just to have some problems that use various functions that you'll find in your calculator that come up within a discrete math context. And these may be functions that you've seen in a calculus context and others that you have not. So the first example we did was to try to figure out how many digits are in this really large number, 2 to the 2012. I think in class we did a slightly different number, but this is the same idea. The main observation is that powers of 10 tell us the first place where we, basically the transition points with numbers of digits. So 10 to the first power, that's 10. That's the first 2-digit number. 10 squared, 100 is the first 3-digit number. 10 cubed is the first 4-digit number. So powers of 10 are our numbers where the number of digits in the evaluation change. So what we're really trying to do here is figure out what number d satisfies this inequality. If we can figure this out, then this number, d to the 10 to the d minus 1, that's the first d-digit number. This is the first d plus 1-digit number. So if we find the value of d that makes this true, then 2 to the 2012 has d digits. Solving this equation, finding out what power of 10 is equivalent to 2 to the 2012 is exactly what logarithms are for. So logarithms are these things that we use to do they're basically the inverses of the exponential functions, and they have various properties, and these properties were all given using base 10. So for example, we know that if we raise a power to another power, then the powers multiply. And if we multiply 10 to the x times 10 to the y, we get 10 to the x plus y. And remember, this is not a great mystery. This is just saying if you have 10 to the x, then you have x tens. 10 to the x means 10 times 10 times 10, x times. 10 to the y means 10 times 10 times 10, y times. And so if you chain together x tens and y tens, then altogether you have x plus y tens. And so that product of x tens and y tens is really just 10 to the x plus y. So that's the sort of reason why all of these rules work. They're really based on nothing more than exponentiation as repeated multiplication. Anyway, for each one of the exponential rules, there's a logarithm rule. So the first exponential rule here is really equivalent, when you turn it around, to this rule about logs. And this is the rule that's going to be helpful to us in the problem that we're addressing. We know that when we have the log of an exponential, so if there's an exponential inside of the log, we can essentially let that exponent come outside the log. So back to the problem, we were trying to find the value x that makes 10 to the x equal 2 to 2012, and we can do that by just taking the log base 10 of both sides of this. And so to do that, here this is really the same thing as x. X is the log base 10 of 2 to the 2012. The rule for exponents we just talked about said that this 2012 can be pulled outside of the log, so instead of the log of 2 to the 2012 we have 2012 times log of 2. Log base 10 of 2 is very easy to calculate. That's just the LOG button on most calculators will give you log base 10 of 2. That's approximately 0.30103. If you multiply 2012 times that, we get 605.67. So the conclusion is that 2 to the 2012 is between 10 to the 605 and 10 to the 606. That's what this tells us. This number is between 605 and 606. We know that this number is the first 606-digit number. 606 digits. And all numbers will continue to have 606 digits until you get to this one. This is the first 607-digit number. So since that's the first 607-digit number, and 2 to the 2012 is not there yet, that means that 2 to the 2012 is a 606-digit number. Now let's try this again with another example. If you'd like to pause the video here and see if you can answer this, that would be a good idea. If we use the same idea as before, we know we need the log base 10, and I'm just going to write LOG of 5 to the 5 to the 5. And because of the rule of exponents, this power here, can be pulled outside of the log. So I have I have 5 to the 5th times the log of 5. Now 5 to the 5th seems like it's a giant number, but it really isn't. If you put it in your calculator, you'll find that's 3,125 times the log of 5, and that's not a hard calculation. That's approximately, let's see, 2184.3. So that means that this giant number, this 5 to the 5 to the 5, is between 10 to the 2184 and 10 to the 2185. And so since this is the first 2,185 digit number, and they don't go up to 2,186 digit numbers until you get to this guy, that means that this number, the answer to our question, is that 5 to the 5 to the 5 is a number with 2,185 digits. So in general, we can present this as a formula. We can say that in order to find the number of digits in a number, x, we are going to take the log of x, and then we're going to drop all of the numbers after the decimal place. So this function here with the bracket with just the bottom half means take the greatest integer less than or equal to that number. And so that's essentially what we were doing. We were just throwing away the stuff after the decimal place, and then we add 1 to that to get the number of digits. This notation with a bracket with the bottom part included only down here, this is called the floor function, and there's another function that corresponds to that called the ceiling function if we include only the parts of the bracket at the top. And that is basically the opposite, where the number goes to the least integer greater than z, greater than or equal to z, rather than the greatest integer less than or equal to z. And so the floor and ceiling functions are very common in different discrete math applications. So here are a few problems to practice. You can take a second if you want to read the examples in the book. Just make sure you understand the definitions, and then pause the video and see if you can answer these. So the floor of 1.23 is the greatest integer that's less than or equal to 1.23, so that would be the number 1. The greatest integer in the floor and ceiling functions do nothing if the input is an integer. So, for example, the floor of 121 is just 121. The floor of -3 is -3. The ceiling of 71 is 71. The ceiling of -13 is -13. So if we happen to put an integer into these guys, then they don't really do anything. Their job is to return an integer value based on the definition. Now, when you put a negative number in, you've got to really think carefully about it, because here the definition of floor is that it's the greatest integer less than or equal to the number that's inside. So inside here is -7.6. The greatest integer that's less than -7.6 is -8. Similarly, the ceiling function, when you put in positive numbers, it basically means just go up to the next number. So the ceiling of 7.01 is 8, because 8 is the least integer that's bigger than 7.01. But if we have a negative number, I have to think carefully about it. The least number that's bigger than -3.2 is -3. So the ceiling function is always giving you an answer that is greater than or equal to the argument, and the floor function is always giving you an answer that's less than or equal to the argument. So regardless of whether it's positive or negative, the floor function returns something that's less than or equal to the argument. The ceiling function returns something that's greater than or equal to the argument. Here's a problem that's similar, but really kind of challenges the technology. If we want to know how many digits the number 500 factorial has, well, that's a really big number, and it's not based on just using exponentiation. It's based on something a little more complicated. 500 factorial means 500 times 499 times 498 all the way down to 1. So you're multiplying 500 numbers together to compute 500 factorial. So we know from our formula before that the log of 500 factorial is going to be the relevant calculation, but we don't have the exponential rule that allows us to pull something outside of the log. What we do have is a rule that says when you take the log of a product, so this log of 500 factorial is really the log of the product of these 500 numbers, we have a rule that says that the log of a product is the sum of the logs. So rather than take the log of this product, that's equivalent to taking the log of 500 plus the log of 499 plus the log of 498 all the way down to the log of 1. So instead of taking the log of this product, I can take the sum of the logs of each of those arguments. And that's the basis of another one of those properties of logarithms. Now this calculation is not particularly easy either because it consists of doing 500 different calculations and adding them up. But we can do it with calculator technology. It's a very easy thing to do with a spreadsheet. You can give yourself 500 rows in a spreadsheet and do these calculations. But the command for on a calculator is given in the book if you want to look it up. And it looks like this. If you're using a TI calculator, you can find the command here. The sum command is in the catalog of functions. The SEQ command is in the catalog of functions. So you have to look up two things in the catalog and then just say log of x. X goes from 1 to 500. And this is basically the equivalent in your TI calculator to the sigma notation that we used. So what's really being calculated here is the sum, k goes from 1 to 500, of the log of k. And that's equal to the log of 500 factorial. So this calculation is too difficult because the input's too big. This calculation is no problem at all. It's just doing 500 separate calculations and adding them up. And once you have that number as 1,134, we can apply the formula we had before, which was to take the floor of 1,034.1 and add 1. So that's 1134 plus 1, or 1135, is the number of digits in 500 factorial. Finally, I wanted to revisit a problem that we had looked at before, very briefly when we were talking about the inclusion-exclusion principle, because the calculation, the underlying calculation we did there really was the same as the floor calculation. How many multiples of 6 are in the set 1 through 2012? Well, the multiples of 6 are 6 times 1, 6 times 2 is 12, 6 times 3 is 18, and so on. So at some point there's going to be a 6 times q, and we want to know what that q is so that that stays less than 2012. So to find that out, I can do the quotient of 2012 divided by 6 and take the floor of that. That gives me 333.3 repeating. The floor then of that number is just 335. So that means that this number here, this quotient, is really 335. In other words, 6 times 335 is the last multiple of 6 that you'll see inside of this set. So since the multiples of 6 run from 6 times 1, 6 times 2, 6 times 3, up to 6 times 335, the answer is there are 335 multiples of 6 in that set. So this really is the same calculation we did before when we found the quotient of the quotient only of the division 2012 divided by 6. The way we used that, if you remember, was with the inclusion-exclusion principle. We said A is the set of, I'll just say multiples of 2, B is the set of multiples of 5, and I'm talking about relative to this set. We said that the size of A union B, that is the number of things that are divisible by 2 or 5, is the things divisible by 2 plus the number of things divisible by 5 minus the number of things that are divisible by both. From this formula we just derived, I know that the number of multiples of 2 is just the floor of 2012 over 2. The number of multiples of 5 in this set is the floor of 2012 divided by 5, and the number that are divisible by both is just the floor of 2012 divided by 10, because the numbers that are multiples of 2 and 5 are really just the same thing as multiples of 10. So that calculation will tell me the answer to this question using the principle of inclusion-exclusion.